We are jumping straight in today with a look at OneThinker, all-in-one reasoning model for image and video by Kaituo Feng and the team. And we're doing that because this paper, it doesn't just push the envelope, it really tries to unify this entire world of visual understanding.
It really does. It's fundamentally challenging the fragmented approach we've all just kind of accepted in multimodal modeling. Historically, if you look at MLLMs, they've been specialists. You'd have a Vision R1 for image stuff, a Video R1 for long videos, a Seg R1 just for segmentation. OneThinker's goal is, well, it's pretty radical. They want a single, unified, multimodal reasoning generalist.
And the big headline is that they actually pulled it off. They've unified capabilities across 10 fundamental visual tasks. We're talking about a model that absorbs knowledge across the full spectrum, blending image and video understanding, everything from, standard Q&A and captioning to really specialized perception tasks, things like object tracking, spatial grounding, temporal grounding, and segmentation, all in one place.
And the breakthrough that makes this all technically possible is a brand new reinforcement learning algorithm they developed. It's called EMA-GRPO. That stands for Exponential Moving Average Group Relative Policy Optimization. And you really need something this sophisticated because standard RL it completely breaks down when you try to mix these wildly different reward types. I mean, think about it. You've got a sparse yes or no reward for a math problem right next to a dense, continuous reward for a bounding box's IOU.
And the numbers really back this approach up. OneThinker delivers strong, and in many cases, superior results across 31 different benchmarks. Just to give you a couple of highlights, the model hits 70.6% on the MMMU benchmark for image QA, which is really tough. And it showed incredible tracking ability with an 84.4 R at 0.5 on GOT10K. It just confirms that this cross-task knowledge transfer isn't just a theory, it's actually happening.
That's right. That holistic generalist capability is exactly what they were aiming for, and the training method is what unlocks it.
Okay, so let's unpack that fragmentation issue a bit more. We know these RL-based reasoning models, using algorithms like GRPO, have led to huge gains, but they are specialists. If you're a researcher or an engineer actually building an application, what's the practical, real-world limitation of this fragmented landscape?
Well, the limitation is cost, both in terms of efficiency and integration. Imagine you're building, say, a real-time monitoring system. You'd need one model to tell you what an object is, that's your QA or captioning. Then a second model to tell you where it is, that's spatial grounding, and then a third to track it for the next 30 seconds. Each of those needs its own model, its own training pipeline, its own inference stack.
Which means a nightmare for deployment, much higher memory usage, and just a lot harder to maintain.
Exactly. Real-world problems are rarely so neat and tidy. They demand simultaneous, unified reasoning. An autonomous agent, for instance, needs to localize an object spatially while tracking its movement temporally and be able to answer a complex question about it. Fragmented models just can't give you that single, instantaneous reasoning ability.
So the core question the paper really tackles is, can we train one single all-in-one model that can handle both image and video understanding across this incredibly diverse set of tasks?
Yes, and the scope they defined is just immense. They're covering 10 fundamental capabilities. We've mentioned question answering and captioning, but then they get deep into the perception tasks. Spatial grounding, which is where is the object in this picture?
Yeah.
Temporal grounding, when does this event happen in the video? And then spatial temporal grounding, tracking, and finally segmentation, defining the exact pixel shape. To do all of that in one model, that requires some serious engineering.
And to handle that massive scope, we have to look at their infrastructure, starting with the data. You can't just train a generalist on narrow, separate data sets.
No, absolutely not. The foundation here is the OneThinker 600K corpus, which is about 600,000 multimodal samples. But I'd argue the quality of the data is even more important than the quantity here. Crucially, they used a very capable proprietary model, Seed 1.5 VL, to annotate high-quality chain of thought, or COTI, data.
Okay, let's just clarify that for everyone listening. Chain of thought data isn't just the final answer, right? It's the step-by-step thinking process. Why is getting that high-quality COTI annotation so vital for this kind of generalist model?
Because it forces the model to learn how to reason, not just what to spit out at the end. When you're tackling 10 different tasks, some needing geometry, others needing temporal logic, the model needs a foundational, internal reasoning structure that can apply to everything. That high-quality COTI annotation process resulted in their initial dataset, OneThinker DAS-FT340K. This first supervised fine-tuning stage is what makes the model smart enough to even benefit from the really complex RL optimization that comes later.
And the mechanism that lets the model handle all these different data types and output formats, from a paragraph of text to a set of coordinates, is this unified interface, the think-answer paradigm.
That structure is really the connective tissue for the whole system. No matter what the task is, the model first has to generate its internal reasoning inside these think tags. So for like a complex geometry problem, the model literally writes out the steps it's taking right there, showing its whole thought process. And this is so important for making sure the reward signal actually reinforces the right reasoning steps.
And then it gives the final result inside the answer tags. But this is where the system gets really clever. For something open-ended like captioning, the answer is just free text. But for all the perception tasks, grounding, tracking, segmentation, that answer is not free text. It has to be a predefined, very strict JSON schema.
And that structured output is critical for two reasons. First, it makes the output instantly usable by other systems, which is a big deal for any real-world application. Second, and this is more important for training, it makes the output instantly verifiable. If the model outputs a bounding box, the system knows exactly where to look in that JSON to pull the coordinates and calculate the IOU score.
It's really the only way you could generate a reliable reward signal across such different outputs, which of course brings us to the core technical problem and the main innovation, EMA-GRPO. We've said standard RL fails here. Walk us through why that happens and what EMA-GRPO does it's so different.
Okay, let's use a quick analogy. Imagine you're training an assistant for two jobs. Task A is do complex long division, and task B is sort these socks by color. For task A, long division, if they succeed, they get 100 points. If they fail, they get 0. It's all or nothing. For task B, sorting socks, success might get them, say, 0.9 points because it's a continuous scale of how well they sorted them.
Okay. So if you just try to optimize both at the same time, the math problem with its huge 100 or nothing swings completely drowns out the tiny, subtle feedback from the sock sorting, which is only varying between like 0.5 and 0.9.
Exactly. That's the heterogeneity problem in a nutshell. Now, the standard RL algorithm, GRPO, it tries to manage this kind of noise by using sample-wise standard deviation normalization. But this creates its own set of problems in a multitask setting. The paper points out two major imbalances.
Okay, let's start with the first one, the intra-task imbalance. You're saying this is a general problem with standard GRPO.
Right. The standard deviation normalization in GRPO tends to favor low variance rollouts. So if a task is hard, the medium difficulty samples, the ones that are actually the most useful for learning, because the model sometimes gets them right and sometimes gets them wrong, those are the ones that get under-optimized. The model gets really good at the easy stuff and at failing the really hard stuff, but that crucial learning zone in the middle gets ignored.
So you stabilize the optimization, but you kind of kill its ability to learn the hard parts. And to fix this, some researchers created Dr. GRPO, which just gets rid of the normalization. But that brings us right back to your first analogy, right? And the second imbalance, intertask imbalance.
Correct. The moment you remove normalization, those sparse reward tasks, our complex math problem, they just take over the whole optimization process. Their gradients are just orders of magnitude larger than the dense, continuous rewards from perception tasks, like a 0.8 IOU score. The gradients from those perception tasks are effectively silenced.
That's a huge problem. The model would basically choose to become a great calculator and completely ignore its vision tasks. So EMA-GRPO is the fix that handles both of these at the same time, using something called task-wise adaptive normalization. How does it give that 100-point reward and that 0.8-point reward equal weight?
The key is context and scale. EMA-GRPO maintains an exponential moving average, an EMA, of the reward's standard deviation. But, and this is the critical part, it calculates and maintains this moving average independently for each task. They use a decay factor, beta, of 0.99, which keeps it stable.
That feels so elegant. So what does that actually mean for the model while it's learning?
It means that within a single task, like MathQA, all the attempts share the same stable normalization scale. That fixes the intertask bias we talked about. It stabilizes things. But because each of the 10 tasks has its own independent scale, it stops the huge gradients from the math problems from squashing the small, dense gradients from the object grounding problems. Each task is optimized on its own terms relative to its own history of difficulty.
Which makes the entire optimization process balanced and stable across what are essentially 10 totally different problems. It really frames unification as primarily an optimization problem in disguise.
It absolutely is. And given that breadth of tasks, it's worth quickly looking at how they're evaluated because the rewards are as complex as the algorithm.
Right, you have the simpler deterministic rewards for rule-based QA where you can just check for correctness. But once you get to the perception tasks with that structured JSON output, the rewards get much more customized.
Right. Take temporal grounding. The model has to output a specific time window in a video, maybe from 15 to 22 seconds, to identify an action. The reward there is calculated using temporal IOU, or TIOU, between the predicted time and the actual time. It's basically how much do those two time windows overlap.
And for spatial grounding, it's the same idea but in 2D space. Finding an object with a bounding box, the metric is spatial IOU, or SIOU. But things get way more complex when you get to segmentation.
Yeah, segmentation is the most complex reward to engineer here. The model isn't actually outputting the full pixel mask. Instead, it predicts a bounding box plus 3 positive points inside the object and 3 negative points outside. Those 6 points in the box are then fed into an external model, SAM2, to generate the final mask.
And that combination is what gets scored.
Correct. And for video segmentation, it also has to predict a keyframe time. The final reward combines the SIU from the box with a Gaussian kernel similarity measured over the distances of those 6 points. It's complicated, but it ensures the reward accurately scores both the localization and the precision of the points that create the final mask.
It's clear the engineering here is incredibly rigorous, but the real test, of course, is performance. Does all this complexity actually translate into results that beat the specialized models they're trying to replace? Let's see the numbers.
The results are very compelling. The OneThinker 8B model consistently outperforms comparable models like Qwen3VL and Struct8B and even specialized models. In general image QA, we see that 70.6% on MMMU and 64.3% on MathVerse.
I think the video results are especially important, just given how hard long context video is.
Absolutely. They hit 79.2% on the long video reason benchmark. This shows a really strong ability to handle long videos, and it's significantly better than models like Video R1SEB-B, which are supposed to be specialists. And the tracking gains are huge. On GOT10K, they got 84.4R at 0.5.
And you mentioned that this tracking evaluation was set up to be even harder than usual.
It was. Most of the prior work used really short video clips, maybe 8 frames, for tracking. OneThinker was tested on 32 frame sequences, which adds a lot more temporal complexity. You need much stronger reasoning about an object's continuity. Getting that 84.4 score under those conditions is a huge validation of its temporal reasoning.
The performance definitely speaks for itself, but the Ablation study is what really proves the technical innovation here. We need to see if EMA-GRPO is the real hero.
And the Ablation, which is Table 9 in the paper, it confirms this without a doubt. The full OneThinker model with EMA-GRPO averaged 69.8% across the QA tasks. When they ran the same model, but with only the initial supervised fine-tuning no RL at all performance dropped to 67.0%. That 2.8% gain is massive in the space.
And what happens if you swap out their special RL algorithm for the older ones?
Replacing EMA-GRPO with standard GRPO, or even doctored GRPO, it caused clear performance drops across all the different task categories. For instance, in the video QA tasks, the performance drop was really substantial with the suboptimal RL methods. It just validates that this task-wise adaptive normalization is essential for getting that balanced, high-performance optimization.
Okay, now this is where it gets really interesting for us researchers.
Yeah.
The analysis of knowledge transfer. They didn't just show that unification works, they showed how the different tasks actually help each other. They tested what happens when they remove specific types of training data.
Yeah. And the results showed some pretty surprising cross-modal benefits. So take grounding. They found that removing spatial grounding data didn't just hurt localization tasks, it actually caused a measurable drop in image QA and segmentation performance.
Wow. So the skill of just figuring out where something is a foundational block you need for general visual questioning.
Exactly. And the same thing happened on the temporal side. Removing temporal grounding data made performance on video QA and object tracking way worse. It suggests the model learns this core temporal perception skill from the grounding task, and then it applies that knowledge to answer complex questions about a video.
But the most compelling link, and maybe the most counterintuitive, was how static image data helped with dynamic video reasoning. Tell me why this is such a big insight.
So when they excluded the image QA data, it caused a severe drop in video QA performance. You might logically assume that video data would be the main driver for video performance, right? But this result shows that the high-quality general reasoning and complex comprehension skills the model learned from static images, which are way easier and cheaper to get transfers directly to the complex dynamic world of video.
So that means we can leverage these huge, high-quality static data sets to boost video capabilities and maybe reduce the need for massive, expensive video annotation efforts. That's a huge deal for data strategy.
It's the defining feature of a true general's knowledge sharing. And on top of that, they showed some preliminary zero-shot generalization ability.
Meaning the model could do tasks it was never explicitly trained on.
Precisely. The model showed it could transfer its skills to completely new tasks, like point tracking, assessing image quality, and even rotated object detection. This initial zero-shot performance, which you can see in Figure 5 of the paper, it strongly suggests that this unified training approach isn't just about hitting high scores, but about fostering genuine generalization that goes beyond its training set.
So this look at OneThinker really shows that building a unified multimodal generalist is, at its heart, an optimization engineering problem. By creating EMA-GRPO to strategically handle all these different reward signals, they've shown that a single unified model can master a huge suite of image and video tasks at the same time, and often it can even beat the specialists.
And that success leads to a really critical question for the whole industry. If unification is this effective, getting state-of-the-art results across so many benchmarks, how much longer will these highly specialized single-task models even be necessary? Will the dedicated trackers and segmenters just be completely replaced by single massive foundation models that use a structured JSON schema as their universal interface to the world?
The era of the generalist might be a lot closer than we think. And now you have the full blueprints for the OneThinker architecture and the EMA-GRPO innovation to think about.